So we talked about special cases when we were foiling. And with foiling, it's not quite as important to remember the special cases because if you don't remember, you can just foil. With factoring, it really can be the same as true for perfect square trinomials. When you are factoring, sometimes you can just remember that it's a special case. And sometimes you can just see, like in the first one from our bell work, that you can find factors of the last one that add to the middle. This was the special case foiling. So for this top one, if we were to see something like this, that just means A plus B, A plus B. And when you foil something like that, what you end up with is the first one squared. And then you end up with a repeated term, A times B, A times B, and then you end up with the last one squared. And so what actually ends up happening is you square the first one, that's your A squared. You square the last one, that's your B squared. And your middle term ends up being the two multiplied together and doubled. So your final answer here looks like this: A squared plus 2AB plus B squared. And that was your special case. And the same thing is true for this one. You just end up with A squared minus 2AB plus B squared. All right. And so with foiling, it's very simple. You can just foil and get that answer if you don't remember to square the first and the last. When you factor, it's sometimes better to recognize that you have a special case. Because if you're looking at factoring and you notice the first one is a perfect square and the last one is a perfect square, you can check the center to see if you just multiplied them together and doubled it, would you get that? And then you know you have a perfect square. And that's true for addition and subtraction. I will say you'll notice that the last term is positive for both of these. Because whether you multiply two negatives or multiply two positives, you're going to get a positive. And so for this perfect square trinomial, it's always positive for that last term. But the center term can be positive or negative. So let's look at factoring these. Look at example. They want us to factor this perfect square trinomial. Now, I will tell you that when I give you all this factoring, I don't tell you what you have. So like on your quiz on Friday, you're going to get all factoring, and I'm not going to say this is a perfect square, this is not, I'm not going to tell you it's a special case. And so when you're trying to find out if it is a special case, you're going to look at the first and last term first. And so x squared, you're going to say, does that have a perfect square root? Yes, any variable to an even number has a perfect square root. The square root of x squared is just x. And then you're going to look at that last term, 16. Does 16 have a perfect square root? What is the square root of 16? 4, all right? And then the next thing I'm going to do is I'm going to say if I multiply these two together, so x times 4 is 4x, and then I double it, 2 times 4x. Is that my middle term? Yes, so this is a perfect square. I use the sign, that's a minus, of my middle term. And this is how I factor it. It's going to be x minus 4, x minus 4. Question? So it says the area of the square shown at the right is 9g squared plus 12g plus 4 centimeters squared. Find the length of the side. Since it's a square, we actually know it's a perfect square because they told us it's a square. All right, so that means each side length has to be the same. For it to be a square, this has to be equivalent to this side as well. And so we're going to look at the terms. So if we take this grouping that they gave us, we are going to look at the first term, which is 9g squared. So does this have a perfect root? What about 9? Does 9 have a perfect root? Yeah, what is it? 3. Any variable that is to an even power is going to have a root. It's just half of that. So it's going to be g. So 3g. And then we're going to look at our last term, which is 4. Does 4 have a perfect root? It does. What is it? 2. And so then we're going to compare it. We're going to say, well, if I take 3g times 2, that's my first and last term, and I double it, I'm going to get 2 times 3 times 2, which is what? 12g. That is my middle term. So that does work. It is a perfect square. I'm going to use the plus sign there. So it's going to be 3g plus 2 squared, which means each side is going to be 3g plus 2. Because this would be my factoring for that trinomial. So the difference of two squares comes from what we did back in section 4, where we have two terms that are identical. And we actually used this when we multiplied large numbers, like 59 times 61. We did 60 plus 1, 60 minus 1, all right? And so when you have a special case like this, if I were to FOIL this, I would get a times b, which is a squared, a times negative b, negative ab, positive b times a, which was positive ab, and then b times negative b would be negative b squared. And for these, the middle terms actually cancel each other out. I have a positive and negative of the same thing, and you end up with the first term squared minus the second term squared. All right? First term squared minus the second term squared. And so when you see this in factoring, so if you're going the other direction, when you see a perfect square minus a perfect square, it's always going to factor to the square root of the first one plus and minus the square root of the second one. And they give this example here, x squared minus 81. Those are both perfect squares. X squared has a perfect root, 81 has a perfect root, and they're subtracted. It's always subtraction for this one. So you just do the plus and minus of the roots, x plus 9, x minus 9. Same thing if there is a leading coefficient here. 16x squared minus 49. 16x squared has a perfect root, 49 has a perfect root, and they're subtracting. So you take the square root, 4x and 7 plus and minus. 4x and 7 plus and minus. So let's look at the first example here. Example 3. Factor x squared minus 64. This is a special case, and you will see it over and over and over all the way through like calculus. So what you're going to look at is you're going to say, does x squared have a perfect root? Does 64 have a perfect root? And the other thing you have to confirm is that is subtraction. That is all true. And so I'm going to take my square root of x squared, which is x, my square root of 64, which is 8, and I'm going to have a plus 8 and a minus 8. And that would be my factoring here. These are very simple, but you do have to remember them because basically it's x squared plus 0x minus 64. And so if you don't remember this is a special case, you typically will not factor it correctly. So go ahead and try those three. Difference of two squares. It does work even if your leading coefficient's not a 1. You just have to make sure that it has a perfect square root. So 4x squared has a perfect square root. 121 has a perfect square root. And so you would take those square roots. 2x would be the square root of 4x squared. 11 would be the square root of 121. And then you're just going to do plus and minus. These are very simple factoring. You just have to remember it when you have it all together. So go ahead and do those three really quickly, and then we're going to do common factor. All right. In this case, when you see that you have two terms and it's subtraction, you're going to check to see if they have roots. Does 10 have a perfect square root? It does not. What about 40? It also does not. But your first step in factoring is to look for a common factor. So then you're going to say, do they have something in common, 10 and 40? Can I take something out of both 10 and 40? I can. What is it? 10. So if I factor out a 10, then I will get x squared minus 4. Now I have two terms, and they are both perfect roots. And so I am going to then continue to factor. So I will leave the 10 out there, and then I will take the roots of these and do plus and minus. So it would say x plus 2, x minus 2. And so often, even when you factor like another way, by grouping, sometimes this works out, then you have to double check and make sure that you don't possibly have something you can keep factoring, like a plus and minus. So go ahead and try those three. All right, so this is just a summary for factoring polynomials. The very first step, so what you always want to look for is the greatest common factor. So whether it is 2 terms, 3 terms, 4 terms, it doesn't matter. You want to look and see if there's something that all of the terms have in common. If the polynomial has 2 terms, you want to look for a difference of 2 squares. If it has 3 terms, you want to look and see it's a special case, which is the product of 2 squares. If it's like a perfect square trinomial. Or you may have to then go to your other factoring that we've done. So where you look for the last term, factors of the last term that add up to the middle, or you may have to go multiply across like we did with the factoring by grouping. If you start out with 4 or more terms, then you're going to do grouping, always. And then they say as a final check, just make sure that you don't have any common factors. At the last, when you have your last terms there, you want to double check and make sure you didn't miss a common factor. For example, if you end up with something like 2x plus 4x minus 5, you probably missed taking a 2 out, because I can take a 2 out of this. And so you should never have, if it says factor completely, you should never have something in either one of those groups that you could still take out, or you didn't factor completely. You probably missed a common factor at the very beginning. Questions on factoring? All right, so tomorrow we're going to do some just factoring practice, and then we're going to have a quiz on Friday. So your quiz review is actually Thursday.